We have described the algorithm, but we don't know now whether it's correct or not. We should prove that it's correct, and there are three parts of this proof. So we need to prove three things. First, we need to prove that algorithm terminates. Who knows, maybe it will happen indefinitely, it will continue indefinitely, and then we don't have a final matching. Second thing is that in the end of the algorithm, we do have a perfect matching, that everybody is paired. And the third thing is stability, that what we get as a perfect matching in the end is really a stable matching. So we need to prove three things, and we will do it one by one. So let's start with termination. It's almost obvious, but let me say it slowly. So let's look at every man. So when he acts, he makes a new proposal, and so he moves in one direction in the list, and there is no way to go back. So he can make at most n proposals, because the proposals are never repeated. And we have n men, so they can make in total only n square proposals, so there is no way to continue longer. And this is rather fast, especially if we compare this with the total number of all possible matchings. So if we have n objects on the left and n objects on the right, you know from combinatorics course that there are n factorial possible one-to-one correspondence between them. And this is much bigger, of course. So n squared is quite practical, but n factorial is infinity for practical reasons. So termination is easy. Now, why at the end we have a perfect matching? It's a bit more complicated. Let's look at it. So imagine it's not the case. So imagine some man remains without a partner after this algorithm. This means that he made proposals to everybody in his list, and each of these proposals was rejected, either immediately rejected or rejected after some time. So all women rejected him either earlier or later. So what does it mean? What does it imply? So we can conclude that all women were married at some point, because if they rejected him, either they were married at the same time immediately, or they were married with him. So anyway, they were married at some point. And we know that for them the situation can only improve. So if they were married, they remain married later. So they remain married until the end. And then of course we get a contradiction, because all women are married and some men is not. And we have the same number of women and men by assumption. So this is how it's called, pigeonhole principle, say that it's not possible. So we have a perfect matching. And last thing is stability. It's also not very difficult, but let's look at it. So assume that it's not stable. The final matching is not stable. This means that there is some dangerous pair at the end of the algorithm. Let's denote this pair MW. So what does it mean? That for M, W is better than his current partner. And for W also, but now we look at M. W is better than the current partner. So this better W was in the list before, because before M proposed to his current partner, he also should have been proposed to W, because it's early in the list. And then W rejected him either immediately or after some time. So W rejected M at some stage, which means that at some time her partner was better, either when she rejected immediately or when she found a better partner than M. So at some time W has a partner that is better than M. And then, since the things improve with time, all the later partners are also better than M. So the pair is not actually dangerous, because the final partner for W is also better than M, so there is no reason for W to change. We get a contradiction with the assumption that there is the pair is dangerous. So this is the proof of stability. Now we have done, and we can formulate and this theorem. A stable matching always exists, and the proof is to use the algorithm to find it. And let's make some remarks about the theorem. So first, as we have seen, the stable matching is not unique. So our algorithm finds one of the stable matching, not the only one. And now it's not clear whether this matching which is found depends on the non-deterministic ordering of the actions. Actually not, and we will see why later. It's more difficult part, but we will see this. And let me stress that this algorithm is extremely unfair. It favors men in a very strong sense. But of course we can consider a symmetric algorithm when women make proposals and men decide whether to accept or reject them. And of course this algorithm will have completely symmetric properties, so it will be unfair, also very unfair, but now in the other direction.